All right. Good morning, everyone. Welcome back to 161, reminding you of your due dates that are on the horizon / today. 3.2 is due today. 3.3 is going to be due Thursday, the 15th. I'm going to talk about the chapter test very, very, very briefly at the end, but I will remind you at this point that 3.6 was already covered as part of the chapter 1 test. Remember, that section was just, quote, misplaced when they updated the textbook version. So this test will end at 3.7. But again, the one or two details that we need to say this early, we'll get to at the end. But for now, we're going to pick up right where we left off in chapter 3.
So just kind of going over some details from 3.3 again. Mainly the synthetic division idea, how it goes. Instead of divide, multiply, subtract, we cut out all the x's. We make sure the bottom is a very specific format. We take the opposite of the number from the bottom and write in that little half box. You write the coefficients of the top to the right, make sure that they were all in descending order based on exponents, make sure no terms were missing, put zeros in their place if necessary. Blank row, bring down the first, then multiply, put that one column to the right, then add, multiply, add, multiply, add. And then the bottom row of numbers, once you're completed, from right to left goes remainder, coefficient of x squared, etc., etc. We have practiced this synthetic division over and over and over already. We've done many of these, several problems actually confirming that it was correct because we had done it via long division, so we weren't just kind of making this stuff up. And then we started talking about the use of this, because moving forward, we're going to start factoring things that you would have never believed were factorable, or at least you would have never learned a true factoring method for it. And it all kind of had to do with this remainder theorem. And specifically, when the remainder was 0, that meant, so the remainder theorem said that the remainder is the output of evaluating a specific number. So if I did synthetic division on x minus 2, that would be like evaluating f of 2 once I got the remainder. But if your remainder is 0, that meant the original problem was factorable, and it means that you can actually factor it by just going x minus that x minus the c, whatever the number was you did the synthetic division on, and then multiply it by the quotient. And we said that's why we really want to do the synthetic division, because when we start having to factor things, we're going to need the quotient in order to do the factoring. This part comes from knowing that 3 was a 0. This part that I've circled, not boxed up, how would you have figured that out without actually doing the synthetic division? And you might be saying, well, Mr. Beckner, I could do long division. Yes, you could, but that's going to take 10 minutes longer. And you're going to be doing this a lot. So we don't want to waste that 10 minutes. We need that 10 minutes. So the last problem we did in this section, I actually assigned you a 0. I said, hey, here's one that works. I promise it works. And if you don't trust me when you do the synthetic division, we prove that it does work. So at least you know I'm not lying to you. But what if I didn't tell you this? What if I just said, solve the equation, and I didn't give you any zeros? Because that's how the real world usually works. We're just told to factor something or solve an equation, and we're not given any hints. So that 3, we have to figure out a way to pick or choose that 3 as one of the possibilities, because we're not just going to know, hey, 3 works. We're going to get a list like plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 12. And then we have to try those out until we actually find one that works. That's going to be the goal in 3.4. All right, so let's get it. 3.4. Zeros of polynomial functions. We are going to establish a way to list all of the possible rational zeros. Now, rational means whole numbers or fractions. It means we can't find any square root solutions this way. We can't find any imaginary solutions this way. So if there are any square root solutions, if there are any imaginary solutions, we would have to find them via another method, which usually they just get factored at the very end, or quadratic formula at the very end, or even completing the square root property. There's always options. But for any polynomial of the form, and that typical form of f of x equals, so the board here, I mean, these were adapted from, notes when we used to see each other in person. That would be f of x is equal to, and how do I want to write these letters? Do I want to use those subnotations? Yes, I do. So a sub n, x to the n. You've seen this before. Plus a sub n minus 1 times x to the n minus 1 plus yada, 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 yada. A sub 2 x squared plus a sub 1 x to the first plus a sub 0. So when I say see the board, that's what I'm talking about, not just the dots, the whole thing I just wrote by hand. Again, this is just a generalized polynomial where each of the little a sub whatevers are your coefficients, so like 5, x to the 7th plus 6, x to the 4th, something like that, where we're just describing that we're going in descending order from largest, one smaller, until we hit no x's. And then the subnotations just match the exponents for the sake of balance. So for all polynomials of this form, just an expanded polynomial in descending order, all possible rational zeros, all the numbers that you might have to test, you'll have to test some of them, maybe not all of them, are plus or minus the ratio of the factors of the constant. So our constant is back here, of course, over the factors of the leading coefficient. And there's our lead coefficient, leading coefficient. So this is a series of values. It's a whole bunch of different options usually. It's plus or minus. So we don't know whether they're positive or negative. We just have to say it could be either and try out and see if the positive one works. If it doesn't, try the negative one. If it doesn't work, then move on to another number. Maybe they both work. Maybe neither work. Maybe one of them works. The factors, so we're going to have to find all the factors of these numbers. It's kind of like the AC method of factoring. It's kind of interesting that there's a parallel there, that we're really worried about the first and last number, because the product of those is kind of what generates the largest possibility. So worrying about the factors of them gives us all the possibilities, if that makes any sense. So the factors of the constant, so this is the top, and then over the leading coefficient, so this is the bottom. So it's your possible rational zeros, which I write as PRZ, are plus or minus the factors of the constant divided by the factors of the leading coefficient. I'm just really abbreviating there. So this is a whole series of numbers. Now, when I do this by hand, I like to write just one big giant fraction. However, when you're doing this in my math lab, you are going to have to separate them by commas. And you may have to write the plus or minus over and over and over and over and over, or you may just need to write all the positives and just all the negatives. So please note that the way I answer things might not be the exact way you have to answer it in my math lab, so adapt. Now, what I tend to call these things, so I don't have to just say factors of constants and factors of the leading coefficient, I like to call the factors of the constant P. So P is the list of all the numbers, and I switched colors there. Let me do that in red. P, constant red, constant red. And then the factors of the leading coefficient, I call a subset Q. You don't have to call them P and Q. You don't have to call them P and Q in that order. You can call them any letters you like. That's just my notation. That's kind of an ugly plus. Let's make that better. This is a very easy idea, believe it or not. And per usual, it might sound really weird and wacky the first time you're looking at it before you see any examples. So let's get to an example and see if it maybe ties things together. The rug will really tie the room together. I know, that's a terrible movie joke. Very specific movie joke, too. List all possible rational zeros for the polynomials one of my colleagues really likes that movie, so I get quotes from it stuck in my head all the time. X to the fourth, f of x equals x to the fourth, minus 3x cubed, plus 9x squared, plus 2x, plus 30. I'm probably one of the more random math teachers out there, I'm sure. why is this teacher making the dude jokes? Sorry, I just spilled a drop of water on my tablet. I want to make sure I get that off. So list all the possible rational zeros for this polynomial. Now, all we're worried about for the possible rational zeros is none of this middle jazz. This problem, I don't care about any of that stuff. I'm going to pretend it's not even there. I'm going to undo this, of course, but I'm only interested in the leading term and the constant. Now, these might be out of order. I could have like an x to the fifth in here somewhere, in which case then I'd be interested in that as the leading term, but that's not the case here. So again, leading term, constant, that's all we care about. I don't care about the fact that it's next to the fourth for now. All I care about is the leading coefficient, which, well, I don't see it. It's a 1, and the constant being a 30. So I don't like leaving that 1 there. I'm just pointing it out. If you need to leave it there, you leave it there. So the P is all the different factors of the constant, which is a 30 at the end. So I'm going to do this the same way I like to write my factor pairs: 1 times 30, 2 times 15, 3 times 10, or 5 times 6. You don't have to list them that way, though. You can just list them linearly. You can go in whatever order you like. And then Q, which is all the factors of the leading coefficient, which is the 1. Well, the only factors of 1 are 1 times 1. And I'm not really going to need the 1 twice. I'm just, again, being very meticulous with listing the factors. This is the entirety of the work. This is all it is. Don't overthink it. So our possible rational zeros are plus or minus. So each of these will represent 2 numbers, a positive version and a negative version. So plus or minus all the factors of the constant, which are 1, 2, 3, 5, 6, 10, 15, and 30. I do like to go in ascending order. 1, 2, 3, 5, 6, 10, 15, 30. Over all the different factors of the leading coefficient. The only factor of the leading coefficient is 1. And if you need to see that in color, I should have done the top in red. I'm going to fix that. Obviously, we don't want to leave anything divided by 1. And dividing by 1 just keeps all those whole. So it's plus or minus 1 comma. I'm actually going to do these divisions. 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 1 is 3. You get the idea. 5, 6, 10, 15, and 30. This is the answer. Now again, in my math lab, you may have to go positive 1, negative 1, positive 2, negative 2. You are probably not going to be able to just use that plus or minus symbol in my math lab, so please understand that. Handwriting, what I boxed up is perfectly fine. In my math lab, you'll have to delineate them, the positives versus the negatives. So it looks like there's 1, 2, 3, 4, 5, 6, 7, 8 possibilities, when in reality, that is 16 possible rational zeros. Excuse me, hold on a second. That is 16 rational zeros because there's the 8 that are positive and then the 8 that are negative. That's a lot of possible rational zeros. Now, spoiler alert, what we're going to have to do with these 16 zeros is synthetic division with them. So we'll put a 1 in the half box, then a negative 1, then a 2, then a negative 2, until we hit 1 that gives us a remainder of 0. That's going to be what we're doing later. Now, with 16 possible rational zeros, that means you may do synthetic division for one problem up to 16 times if I ask you to find all the zeros of this one. Now, I didn't ask you for that. We'll get there later. But that's a lot of testing. And you go, well, Mr. Beckner, it takes me like 2 or 3 minutes to do each of these. So if I got to do 16, it's like a half an hour. Are you kidding me? What kind of mean teacher are you? Well, don't worry. First of all, most problems are designed that if you go in an ascending order of that testing, you'll find one in 3 or 4 passes. Second of all, I will teach you a way you can use your technology to push you in the right direction. But remember, technology is not there to give you the answer. You would still have to show all your work. No work, no credit. All right. B. F of x equals 2x to the 7th minus 3x to the 4th plus 8x minus 10. All right. Oh, 4-term polynomial. Doesn't matter how many terms it has. Just make sure you've got the leading term accounted for, which is the 2x to the 7th. And that the constant at the end, this is the minus 10. So it is the first and last that it will give us our set of p's and q's. So mind your p's and q's. Now you don't even need to write the minus for the 10 here. I know traditional factoring, I would write that minus, but all I'm worried about is just the number, because in the end, you're going to be putting a plus or minus in here anyways to account for all possibilities. Well, 10 is 1 times 10 or 2 times 5. So that's all the factors of 10. For the leading coefficient, which is 2, there are 2 factors of 2, which are 1 and 2. So our possible rational zeros, and these are the possible ones that could spit out a remainder of 0. I'm not saying all 16 of these do. It's only at most 4 of them, and I can't even guarantee that it is 4 of them, because these are just the rational zeros. You can also have irrational zeros, which again means square roots and imaginary numbers. All right, so plus or minus all the different red numbers, which are 1, 2, 5, and 10, over all of the different blue numbers, which were the leading coefficient numbers, which are 1 and 2. 1 comma 2. So this is plus or minus. Do all the reds over the blue 1, then do all the reds over the blue 2. So we will have some reductions to do. So this is 1 over 1, again, red over blue, 2 over 1, 5 over 1, and 10 over 1. All I've used is the 1 from the bottom. I used all the red tops though. So I used all of these over that. Now I need to do the same thing with the 2 in the bottom. So use all of the red numbers, the 1, 2, 5, and 10, but now over the 2 instead. So a half, 2 halves, 5 halves, and 10 halves. Now some of those are reducible. Well, most of them are reducible more specifically. That's plus or minus, that's 1, 2, 5, and 10. And let me just pick another color. Point out a couple of these over here. 2 over 2, that's 1, which we've already listed as a possibility, which means I don't need to write it again. So I skip it. 5 over 2, well, that is going to need to be up here. 10, and the 1 over 2 as well is going to need to be up there, but the 2 over 2 is a repeat. That's just 1, so I skip it. Then 10 halves is really 5, which we've already listed, so I'll skip it. I will skip writing these, not for any particular crazy reason, but just because we already saw them from the first 4. So you can get some repeats, and you don't need to list repeats a repeated number of times. But I still do need to get the 1 half and the 5 halves. So there are our possible rational zeros for the second one. 1, 2, 3, 4, 5, 6. But when you consider the plus or minus, that's really 12 possible rational zeros that in the grand scheme of things, you would be doing synthetic division with until you found a remainder of 0. You might have to do all 12, maybe you only do 2 or 3. Just depends on the problem. Now, I want to point out something. These problems like here, when I ask you to list the possible rational zeros, this is exactly how a test question could go. It could look like A or it could look like B. I could give you more factors from Q. If this, say this 2 was like a 50, you would have a lot more options for that. You'd have 1 times 50, 2 times 25, and 5 times 10, which means you'd have to do a lot more separated cases because you'd have to do over the 1, then over the 2, then over the 5, the 10, the 25, and the 50. That's perfectly fine for listing possible rational zeros. I can give you that as a problem. Moving forward into what we're about to do, actually finding those zeros, in terms of test questions, I will not make you test any fractional points on a test. Again, it's for a problem where you just list the possible rational zeros, this is perfectly okay for a test. But coming up, what we're about to do, I will make sure that your test questions, finding the zeros, you don't have to worry about fractions. And I'll do that by just making sure for the next type of problem, the leading coefficient is always a 1. Because plugging fractions into synthetic divisions means you're going to be adding and multiplying fractions, which involves LCDs, which is just more time consuming. I'm not saying these problems don't exist in the real world, they absolutely do, but we've got a limited amount of time left in the semester. I got to make sure we get down to just brass tacks. So I'm trying to eliminate one complication. You're welcome. All right, let's put this back on blue, and let's get to one of the strongest methods of finding zeros or just factoring in existence. This is a factoring method. It's not necessarily called a factoring method, but that is one of the two goals of it. The primary goal it's used for is finding zeros of any polynomial, not just a quadratic, not just a cubic that can be factored by grouping, but anything by just doing this, what feels like blind testing, coming up with a list of numbers that may work, trying them out until you find one that works, and then breaking it down to something simpler, and then lather, rinse, wash, repeat. So that thing we were doing, finding the possible rational zeros, is known as the rational zero test. If I didn't say that out loud, I know it was written down. So we do the rational zero test to find all possible rational zeros. That's all the factors of the constant over all the factors of the leading coefficient. That's just listing the plus or minus, da 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 da. So step one is what we did for the last two examples. Step two is that thing I kept alluding to. Use synthetic division to find a possible rational zero that has a remainder of zero. Because if you get a remainder of zero, that means that the polynomial is factorable using that zero. So if 3 is a zero, x minus 3 is a factor. Remember, they take opposite signs that way. If negative 3 is a zero, then x plus 3 is a factor. Now, I've given you a hint for the synthetic division process. The problems that I give, you will generally find a possible rational zero after no more than 3 or 4 attempts. If you do the 1, then the negative 1, then the 2, then the negative 2, then the 5, then the negative 5, then the 10, then the negative 10. Just work your way up in absolutes. I will mention there are other theories or theorems that help you eliminate some of these possibilities, but that theorem is fairly time consuming to actually go through, and it doesn't, the one that we do in here, or would do in here if it was part of the curriculum, doesn't even pick off most of the problematic ones except like 20% of the time, so you usually just end up wasting time. I will give you a technology version of getting one that works instantly. That way you don't have to just do failed synthetic division after failed synthetic division. But let's not do that yet. We'll do that when we get to an example. All right, so once you have a zero that works, a zero that spits out a remainder of zero, because that means it's a zero, you factor the polynomial. So if c was your zero, x minus c is your factor. Then remember, you need the quotient from the synthetic division, because that gives you the other factor. If you just plug these numbers into the function and see that it spits out zero, it's cool that you know that it is a zero, but it does not give you the other factor of the function, which is critical. So you must do synthetic division, or if you really want to hate your life, long division, because imagine if you have to do 4 long divisions just to find one that works, and then you've barely even started the problem. That sounds horrible. That's 40 minutes right there. All right, so once you do that, if that quotient isn't factorable, generally meaning it's got a degree of 3 or higher, if it's quadratic, then you're going to factor it or do the quadratic formula or complete the square or square root property, which is the plus or minus square, whatever it would work for it. But if that's a cubic or higher, usually you're going to have to just go back to step 2, which is do the synthetic division to find one that spits out a remainder of 0. So there's a repeating process here. You're just going to keep doing this, but there's a couple of details that are important that will help you not make a mistake. So let me kind of skip this for now. So I'm down here. If you do have to repeat step 2, which very often you will, don't test zeros that already failed. So let's say your possible rational zeros are 1, -1, 2, -2, 5, -5. And you tried out 1 and it failed. You tried out -1 and it failed. You tried out 2 and it worked. The 1 and the negative 1 will always fail for this problem. You don't have to worry about trying them again. And when you do try them, you're only worried about plugging these into the quotient. You don't need to go back to the original polynomial. You need to do this in the quotient. So make sure that you're not going back to the original polynomial. Do this in the quotient, because if a 0 worked in the original polynomial, it's going to keep working. You'll just see that 2 work over and over and over and over and over. Now notice I said don't test zeros that already failed. I didn't say don't test zeros that worked, because these zeros could have a multiplicity of 2 or 3 or 4, so they could work again in the quotient. And again, make sure you're doing this in the quotient. Q of x just means quotient. Q of x, same thing. You can actually also start a new list of possible rational zeros for the quotient. If your leading coefficient and constant have changed in there, maybe you'll go from having 10 possible rational zeros to only, say, 4. So that can happen sometimes. It just means there's less numbers to worry about. So maybe before you had 30 and negative 30 to work on, but now the constant for the quotient is just 15. That means 30 and negative 30 are out. You don't even have to attempt with them. So that's what you do if your quotient is not factorable. And if it is factorable, then factor. If it's an x squared and it's not factorable, try the quadratic formula or completing the square, whichever you like. This, again, is the ultimate solving polynomial method for this entire Pre-Calc 1 course. Now, what's interesting is, I'm always honest about what we continue to do over and over and what we don't. We won't do this in Chapter 4 at all, mainly because we won't be dealing with polynomials. We'll be dealing with what we call exponential equations. But in Pre-Calc 2, the occasional time you're dealing with polynomials, you never need this method. In Calc 1, in the Calc 1s that I've taught, I've actually never seen this method needed. So you might be thinking, oh, well, why are you teaching this? If I'm not going to need this until something past calculus, why am I learning it? Because this is an amazing method. We've said how factoring only solves like 2 or 3% of the problems in the world, maybe 10% if you're exaggerating. And then we said, all right, well, then we have the quadratic formula. Well, after the quadratic formula, there is a cubic formula, but it's a nightmare to look at. It doesn't make any sense to anybody who doesn't practice it for a month. Then after that, there's only one more formula. If you have a 5th order or 6th order or 7th order polynomial, there is no generic formula. And again, up to the ones where it kind of stops, they just turn into nightmare fuel. It's unbelievably complicated. So we really like to fall back on factoring when we can, and this is kind of like a synthetic factoring. It's factoring without actually really doing factoring. It's finding the 0 and then factoring based on the 0. So this is an awesome way of thinking, because it's kind of like Jeopardy. We get the answer, but then we have to ask the question. That's kind of like what it is. The 0 is the answer, the factor being the question. It's working in an unusual order. All right. So we have, that's for much later. In fact, I'm going to need a lot of space. Example 2. Find all zeros f of x. Now, I could do the exact same problem and give different instructions. I can say factor f of x, and it could end up being the exact same problem. So f of x equals x cubed plus 2x squared minus 5x minus 6. Oh, a 4-term polynomial that's cubic. Let me just factor it. Good luck factoring it, because factor by grouping doesn't work, and I haven't taught you a method besides factor by grouping for a 4-term 3rd-order polynomial. So if I want to find the zeros, I need to do something else. We need this method, because I haven't taught you. I'm not saying there isn't a factoring method to factor this, but whatever factoring method that exists for this is much more complicated, believe it or not, than what we're about to do. And especially since that method would only be valid for this, if I put in an extra term, that method's out now. If I go to a higher degree, that method's out. Whereas this right here works for pretty much every single solitary case in the world you can imagine. All right, so first, list the possible rational zeros, which are plus or minus the factors of the constant, which are this minus 6. So the factors of the constant are 1, 2, 3, 6, over the factors of the leading coefficient, which we don't see a number there, which means it's a 1. So over 1. It's always constant over leading coefficient. If you get those upside down, you're going to have a bad time. Because as I've already said, I'm going to make sure for test problems that these are all whole numbers, and these are all whole numbers. Again, in the real world, they could be fractions, but fractions are a bigger pain in the butt to do synthetic division with. So there are 4 values here with the plus or minus. That means there are 8 possible rational zeros. So that means we could be doing synthetic division up to 8 times. I'm not saying we will, I'm saying it might happen. So the second step, do synthetic division on these values until you find one that's a remainder of 0. So this is just blind, shot in the dark. We're going to try the 1, then the negative 1. Then the 2, then the negative 2, the 3, the negative 3, the 6, and the negative 6 until we find one that works. So let's try the positive 1 first. Now remember, the possible rational zeros are the exact numbers that go in the half box. The factor would change sign. This is like us trying to divide by x minus 1. Again, the division and the factor have the opposite sign. The 0 and what goes in the half box have the same sign. All right, then coefficients to the right, so 1, 2, negative 5, negative 6. I hope you've been practicing this because I'm going to go significantly quicker with my synthetic division today. If you haven't practiced, go back and do 100 of these and then come back. All right, not going to change colors either. Bring down the first one. That's a 1. Then it goes multiply. We multiply these two things, and then that answer will go here, which is not 0. I'm just saying it goes here. 1 times the 1 is 1. And then you add these, and the answer goes here. 2 plus 1 is 3. And then you just keep doing that. 3 times 1 is 3. Negative 5 plus 3 is negative 2. Negative 2 times 1 is negative 2. And negative 6 plus negative 2 is negative 8. So we're done with the synthetic division. And we're supposed to do this until we find a remainder of 0. Well, guess what? Negative 8 is not 0. You don't have to write this, but that's just a sign from me saying, nope, 1 failed. Positive 1 fails now. It will continue to fail for this function. So if we had to repeat this process, we would not test positive 1 anymore. Well, up to negative 1. We tried our best and we failed miserably. There's a rest of a Homer Simpson quote there, but I'm not going to say it because I don't truly believe it, and I'm recording this on the internet. We didn't fail miserably. The point is you have to try. Bring the 1 down. 1 times negative 1 is negative 1. 2 plus negative 1 is positive 1. 1 times negative 1 is negative 1. Negative 5 plus negative 1 is negative 6. Negative 6 times negative 1 is positive 6. Negative 6 plus 6 is 0. And that is exactly what we want to see. That is the goal. The goal is to get a remainder of 0. Because of the remainder theorem, because of the factor theorem. Scrolling back up for a hot second, we said that if there were, first the remainder theorem, which said the evaluation of a number is the remainder via synthetic division. And then the factor theorem said that if that remainder was 0, if the output is 0, then x minus that original input, or what we put in the half box, is the factor. And then the quotient is the other factor. So we just found a factor. So what we have here is that x equals negative 1 is a 0. If you plug negative 1 in here, if you plug negative 1 here, here, and here, and do your exponents and all that jazz appropriately, that thing will be 0. If negative 1 is a 0, then x plus 1, so x plus 1 is a factor. If you don't believe me, once we get the factored form, I'll show you how that works. It's just all about a sign change. So f of x, the original function, can now be rewritten. This I'm going to rewrite in a factored form, not completely factored, but a factored form. Here's the x plus 1 that is a factor because negative 1 was a 0. And then this is supposed to be times the quotient, which the quotient is based off of, I didn't mean to circle the 0 too. The quotient is based off of these three numbers here, because from right to left, that goes remainder, constant, x coefficient, x squared coefficient. So the quotient is, I'll write the numbers here to be very meticulous for now, 1x squared plus 1x minus 6. Again, just knowing that negative 1 is a 0, if I plug, why can't I just plug the 1 in? Plug in 1 and spit out negative 8, so it fails. Plug in negative 1 here, it spits out 0. Okay, so that means x plus 1 is a factor. But again, just plugging it into the function would have never given you this, and that is critical for moving forward. So in your mind, what you're going to do is, you no longer really care what the original function is. Don't look at it, don't use synthetic division on it again. It's gone. Now, I'm not going to leave it permanently erased, but again, in your head, that's gone. What you should be focusing on now is the quotient. So focus on the quotient continuing. So now what we're trying to do is find the zeros of 1x squared plus x minus 6. Now you might say, okay, well, let's go back to the possible rational zeros. We threw positive 1 out. It didn't work then, it won't work now, but negative 1 did work, so we'd have to try negative 1 again. And I'm not going to actually do this. I'm going to erase what I'm about to write. But here's the way I would do it if I wanted to continue synthetic division. I would be using the coefficients of the quotient now here, the 1, and the negative 6. Some people even like to just kind of go up here and put the negative 1 here. I don't really like doing that because if it fails, you're going to get all jumbled up. But again, the quotient numbers are what we're now doing in the synthetic division. That's why this is not being used anymore. We're using this instead. And then we would keep doing again. I'm going to erase this. This is not what I'm actually going to do. The reason I'm not going to do it is because this is quadratic, which means we've got a really good set of factoring methods for that. And if those fail, we go to the quadratic formula, or if we really like it, completing the square. So I'm just going to try factoring the quotient. So again, our function was x plus 1 times x squared plus x minus 6. That negative 6 has factor pairs of 1 times 6 or 2 times 3. To make sure the difference comes out to a positive 1, we choose the 2 and 3. To make sure it comes out positive, it's a negative 2 and a positive 3. Again, I'm not here to teach factoring. You are supposed to be excellent with that on your own. Keep practicing it if you need. All right, so that's the factored form of the quotient. So f of x is equal to x plus 1 times x minus 2 times x plus 3. That's the function in a factored form. So if I had given you the instructions to just factor this polynomial, that would be the answer. This is factored. However, I asked for the zeros, which means we've got to take this the one step further, which is typical. And we set the function equal to 0, and then just zero product rule this thing to death. One of which we already know. The first one, we already know the x plus 1 being 0. Tells us x equals negative 1. That just agrees with what we set up here. So I generally won't reinvent the wheel when I move forward with these. With x minus 2 being 0, that says x is equal to positive 2. And with x plus 3 being a 0, x plus 3 being 0, subtract 3 on both sides and you get x equals negative 3. See, the factored form always has an opposite sign to the 0 because you have to algebraically move it from one side to the other. There we go. That's terrible. I'm just going to write to the side. So x equals negative 1, 2, and negative 3 are our zeros. Make sure my math lab doesn't ask for them in any kind of order. If it asks for them in ascending order or descending order, if you have the zeros right and marks you wrong on a test, I'll give you full credit for that. I do not care if you misorder them. It's all about getting them. My knuckles popping. If you heard that, which you probably did, my mic is very sensitive. I need a gate for this thing. So we have just factored something by a non-traditional factoring method that would have worked for much more complicated polynomials. Again, there is a traditional factoring method for this style polynomial. It's complicated enough on its own, and it only works for a very specific type of polynomial. What we just did works for pretty much every polynomial in existence. We love techniques that work for pretty much anything. The only types they don't work on is if there are no whole zeros or fraction zeros. So if all of your zeros are like square root of 2 and 5i, negative 5i, this test would fail because we're only finding the possible rational zeros, which means whole numbers and fractions. All right, so we only had to do synthetic division twice. It was possible we had to do it 8 times if we just done this in a terrible order. But one thing I want to point out before I show you the technology cheat, if you had thrown 2 in the synthetic division, if I had done a 2 here, at the end, the remainder would have been a 0. If I had done a negative 3 here, again, all the numbers in the middle would look different, but at the end, the remainder would be 0. So it's not like we absolutely had to use the negative 1. If we used the 2, that would have just given us a different quotient, which would have then just be factorable a little differently, but at the end of the day, we would have gotten the same factored form. So don't think you have to pick off a particular 0. The reason I tell you to go in this kind of ascending order, 1, negative 1, 2, negative 2, etc., is because I generally make it so there's a small valued 0. That way you don't just go, well, I'll try the 6 next. Let me do the negative 3 next. Well, how about negative 2 next? How about positive 30 next? You do that, it might be the 30th or 40th one when you find your 0. All right, so here's the thing I love showing my students, but at the same time I hate showing my students, because I know what some of you are going to do is when you get to the test, you're just going to let the calculator do all your work for you. You're going to get the answer right, and then when I go and look at your work, because I will, I'm going to see that you didn't do any of this jazz, and then I got to go and take all the credit from you, even though you had the right answer, but because you used technology as a crutch and not as an assistant. So I'm about to use this as an assistant to show you a way that you can see a 0 that actually works without having to test it. You still have to go and do the synthetic division, but that'll avoid you, let's say 1, negative 1, 2, negative 2, 4, negative 4, 6, negative 6, 12, negative 12, those all fail, and you're getting frustrated. You're like, man, I've already done 8 of these. When am I going to find one that works? The calculator can point you to one that works immediately. Go to your y equals, go x cubed, just type in the function, plus 2x squared, minus 5x minus 6. Make sure you're in a standard zoom, hit graph. I can see all 3 of my zeros just looking at this. Remember, zeros are your x-intercepts. So our zeros are right here, and right here. So now I know which ones actually work. However, it's not a guarantee that these are nice, pretty numbers. If this was something like square root of 2, your calculator is not going to tell you square root of 2. If it's negative 7.351, you're going to have a very, very difficult time picking that off. So you got to find at least one of these that's a nice whole number, or, at worst case, like a fraction that's a half or a quarter. But I've already said I'll try and make sure that those don't happen on test questions. All right, so those are my zeros. If I hit the trace button, I can smoothly go along and see, okay, well, here's one. Negative 0.8, I'm focusing on the x value, negative 0.85, negative 1.0. So it's probably negative 1, but I'm not confirming it yet. To confirm it, what I got to do after I hit traces, just type negative 1 and hit enter, and it will show me the exact y value for negative 1. So when x is negative 1, the y value is 0. Boom, I just confirmed that negative 1 works. So I did synthetic division with positive 1 here. Look at what happens at positive 1. So here's positive 1 on the x-axis. It's all the way down here. That is clearly not a 0. And if you type positive 1, you can see you get a y value of negative 8. Oh, look at that, negative 8. That's not 0, so positive 1 fails. So this is how I'm telling you you can use technology to point you at the right direction. I can tell 1 isn't going to work because it doesn't cross the axis at 1. I can tell negative 1 works because it does cross the axis. Oh, I cross again here. If I just move over, That looks like it's around 2. I could confirm that by trying 2, and it is exactly 2. So I could do the synthetic division with the original polynomial with 2 instead of -1. It would give me a different quotient, which would lead to different factors, but ultimately all 3 of the same factors and all 3 of the same zeros would be there. Or you say, oh, how about this one over here? What's that? So you can trace over to it, and it looks like it's about -3 in that ballpark. So if you type -3, it is that nice whole number. So we could do the synthetic division with -3, excuse me, and it would spit out a 0, and then we get our quadratic, and we could factor. Now, this problem is really kind of convenient in a way, but also inconvenient for you as a student because, oh, I got -3, -1, and +2. I can actually pick off all 3 of the zeros. So me, as a student not doing what their teacher is asking, with this problem, I can just go in my math lab and type -3, -1, and 2, and boom, the test gives me full credit. But I've already told you, I will be looking at your work for this, and no work means absolutely no credit. If I know your calculator has done the entire job for you, I will award you nothing. The second issue is you can't always pick these off exactly because they aren't always whole numbers. You will see zeros moving forward that are square root of 2 or negative square root of 5 or imaginary zeros like 3 plus 5i and 3 minus 5i. This calculator is not going to tell you that. The only way you can pick it off is by getting the one that actually does work, the whole number, getting it down to a quadratic, and then factoring or quadratic formulating it. So this won't always tell you all of the zeros. So that's the twofold issue. First, your teacher is mean and is going to look for your work. Second, it's not always going to tell you all of them. So be careful with that. And I don't do that to be mean. I do that to make sure that you are actually understanding the process. All right, B, x cubed, 7x squared. That's a terrible placement of the square. Plus 11x minus 3? Yes, minus 3. How are we on time? 20 minutes and some change, 25 minutes, yeah. So first thing, possible rational zeros. Again, the possible rational zeros are not always all of the zeros. Spoiler alerts. But this is where we take the factors of the constant, which is the -3, over the factors of the leading coefficient, which is a 1. The factors of -3 are 1 and 3. The factors of 1 are 1 times 1, so just 1. So your possible rational zeros are just plus or minus 1 and 3. There's only 4 of these. It's not a very large list. And coincidentally, the less options for your possible rational zeros, the more likely you are to have irrational zeros, which means square roots, imaginary numbers, whatever. But it's not a guarantee. So we got 4 to check at most. 1, -1, then 3, then -3. Now you might go, all right, Mr. Beckner, just use your calculator to push you in the right direction. Yes, you can, but I want to make sure we're continuing to practice this synthetic division like a beast. So let's try out the +1. Coefficients to the right, they are in descending order. They don't have to be, so pay attention. 1, 7, 11, -3. Bring down the first one. Why did I go back to black? I'm just trying to keep all my work in blue. I'm not going to change anything, just the color. 1, 7, 11, -3. There we go. So bring down the 1. Multiply by the 1. 1 times 1 is 1. 7 plus 1 is 8. 8 times 1 is 8. 11 plus 8 is 19. 19 times 1 is 19. -3 plus 19 is 16, which ain't 0. Remember, the goal is 0. Don't think you can figure out whether this is going to spit out a 0 initially. I've been doing this for more than 2 decades, and I still have a hard time predicting them. I get lucky every now and then in the prediction, but I've been wrong more than I've been right, admittedly. I got to do all the work, so you probably do too. All right, so let's try the -1. 1 failed now, it will always fail. Don't ever try 1 again for this polynomial or its quotient. Bring down the 1. 1 times -1 is -1. 7 plus -1 is 6. 6 times -1 is -6. 11 minus 6 is 5. 5 times -1 is -5. -3 plus -5 is -8, which is not 0, so it fails. Let me see if I can squish a third one over here. So let's try the 3. We're already halfway done with our options. It's not looking so good, is it? 1, 7, 11, negative 3. Bring down the 1. 1 times 3 is 3. 7 plus 3 is 10. 10 times 3 is 30. 11 plus 30 is 41. 41 times 3 is 123. 123 plus negative 3, I said it backwards order, but it doesn't matter, is 120, which is not 0. Oh, man. Oh, Mr. Beckner, you told me at least one of them has to work. I promise it does. So I think you can already guess that negative 3 works unless we made a mistake somewhere, which we didn't. I'm not saying you wouldn't have, but we definitely didn't here. All right, fingers crossed. 1, 7, 11, negative 3. Space, plus sign. Bring down the 1. 1 times negative 3 is negative 3. 7 minus 3 is 4. 4 times negative 3 is negative 12. 11 minus 12 is negative 1. Negative 1 times negative 3 is positive 3. Oh, look at that. We got our 0. Whew. Wipe the sweat off your forehead. We made it. So only one of these actually works. Now this negative 3 could work over and over and over and over and over. Potentially, it could have a multiplicity of 2 or 3. But for now, let's just take what we have. Maybe you said, Mr. Beckner, I'm not going to do all those failed attempts. I'm just going to go to my calculator like you taught me, and I go x to the third plus 7x squared plus 11x minus 3. And then I hit my graph. And I can see that I've got 1, 2, 3 zeros. And I can tell that 1, which would be right here, doesn't work because that point's way up here. 1 fails. 3 is somewhere way up here because this thing just keeps on trucking in an upward manner. So 3 definitely doesn't work. And then you go, okay, well, out of the negative 1 and negative 3, here's negative 1. Negative 1 is down here, so that doesn't work. This looks like negative 3. I'll prove it in a minute. But look at this. This point right here and this point right here, that's about 0. This is about negative 4. Let's see what they are on my calculator. I can probably trace that out. It's just probably 0. So if I type in 0, negative 3, so that's not it. If I move to the right, I'm a little closer, 0.2, that's still a negative y value. If I go right a little more, I get a positive y value, which means it's somewhere between 0.42 and 0.21. So maybe you just, let me try 0.3. That's too big, so let me try 0.28. Still too big. Let me try 0.25. Still too big. Let's try 0.22. Oh, too small, so let's try 0.23. And that was too small. Oh, I hit enter on accident. But that was a negative. You can see how that just gets ridiculous because that means it's an irrational number or just a complicated fraction that you're not going to pick off on your own. So go away from that one. Now this looks like it's about in the ballpark of negative 3. And it is. So I got one that works. So my calculator, again, could just give me a way of not doing all of this synthetic division testing and only doing this. And that's perfectly fine. If your work only has the synthetic division that works, I am okay with that. I don't need to see the failed attempts. I'm just going to know that you use your calculator to push you in the right direction, which is what I've taught you to do. Now, if you don't have a graphing calculator, you're going to have to do the failed attempts, obviously. And just by the way, this one, it looks like it's over at negative 4. If you type negative 4, it doesn't work. That's a 1. So maybe it's, negative 4.1. Well, you're going to have that same issue. You're not going to be able to find it. All right, but that's okay. We don't need it. We got the negative 3 that worked. So that means x equals negative 3 is a 0, which also means that x plus 3 is a factor. I didn't write the words is in there. That's okay. So before I write so, let's identify the quotient. From right to left, that's the remainder, the constant, the coefficient of x and x squared. Some people even like to write their quotient before they move forward, that it would be 1x squared plus 4x minus 1, which means our polynomial is now, instead of writing what I had in black originally, I can write the factor we already found of x plus 3 in a nice linear factor times the quotient of x squared plus 4x minus 1. Now this is quadratic, which means while you can still do this possible rational zero stuff and the synthetic division stuff, you don't have to. It's much easier to factor traditionally or quadratic formula it. Now, if you try and factor this, -1 is 1 times 1. There is no way to subtract 1 and have it be 4, so it's prime. So this piece is not factorable traditionally, which means we need to use the quadratic formula, or if you prefer, completing the square. Because remember, what we're doing here is we are setting this function equal to 0. That's the whole thing. We are setting this equal to 0, which is why we're allowed to quadratic formula this, to find its zeros. So for x squared plus 4x minus 1 equals 0, it's a terrible looking 0, your a is 1, your b is 4, and your c is -1. So therefore the solutions are, remember this formula, I told you never get to forget it, -b, so -4, plus or minus, big square root, and then it goes b squared minus 4ac, so 4 squared minus 4 times a, which is 1, times c, which is -1, all over 2a, which is 2 times 1. And from here, it's just arithmetic. It's -4 plus or minus the square root of 16. Now that's -4 times 1 times -1, which is a plus 4, all over 2 times 1 is 2. 16 plus 4 is 20, so that's -4 plus or minus the square root of 20, all over 2. But you can break down the square root of 20 as 4 times 5 because we know the square root of 4. So you have to do that. Then you take the square root of the 4. I'm going to do that in red so you can tell where it came from. So -4. Why did I write a 2 there? Excuse me. Dang it, I was supposed to still have a 4 there. The 2's outside. So -4 plus or minus 2 square root of 5 all over 2, because the square root of 4 is 2. And now, all of the outer numbers have a common factor, so we can reduce them by 2. So we can divide all by 2. You can show the factoring and canceling if you need to. A lot of people will just go, oh, this becomes a -2, this becomes a 1, and this becomes a 1. I just don't want to leave the crossing there. Actually, yeah, that's fine. No, I don't want to leave it. But you saw it there. So what we get is -2 plus or minus, if that's a 1, we don't need to write it, square root of 5. If the bottom's a 1, we don't need to write over 1. It's just the top. So there's our other 2 zeros. We found one of the zeros here. We found the other 2 here. Now, they're pretty separated, so it's probably a good idea to just combine all of them into one answer. So x equals, the first one we found was -3, comma, then -2 plus or minus square root of 5. Now again, in my math lab, you're probably going to have to write -2 plus square root of 5, comma, -2 minus square root of 5. That is also acceptable. And probably the way you have to do it in my math app, as I've mentioned every time. See, 2 of these zeros were irrational. Again, that means square roots or imaginary numbers, because imaginary numbers have square roots in them. Square root of -1 specifically. You cannot find these from the possible rational zeros, because the possible rational zeros are only things without square roots and i's, only whole numbers or fractions. So once again, the possible rational zero thing is not the end-all be-all. you are very likely, I'd say in about half the problems, to find zeros like this. So what some students try and do is just say, oh, I'm going to do synthetic division on 1, -1, 3, and -3. And they'd say, oh, -3 is the only one that works, so they'll stop here. Because, well, Mr. Beckner, I've tested all the possibilities. This is the only one that works, so that's the only zero. No, that's the only rational zero. Because you still have to, do the rest of the factoring stuff. You get down to quadratic. We tried factoring. It failed, so quadratic formula. That quadratic formula is what's going to pick up the square root and imaginary solutions. Now, there are polynomials out there in the real world where all of the zeros have square roots or i's. We don't give you them in here because you would not be able to even start the problem. You would need another method that is extremely advanced. I'll even admit that I never really fully learned it because there was never really a reason to. It was there's reasonings behind that, but we don't need to get into it. All right. How are we on time? About 12 minutes. We got time for one more. We will not finish this section. We're like one problem shy of finishing the section. That's a slight annoyance, but it's not the end of the world. Can I fit all this here? I think I can. F of x equals x to the third minus 4x squared plus 8x minus 5. Once again, these don't have to be in descending order, but I'm just getting to the point. So your possible rational zeros are plus or minus all the different factors of the constant, which is 5, so 1 and 5, over all the different factors of the leading coefficient, which is a 1, so 1 times 1. But you don't need to write the 1 twice. 1 divided by 1 is 1, 5 divided by 1 is 5, so plus or minus 1 and 5. Again, only 4 possible rational zeros. Maybe 3 of these 4 work. Maybe 2 of them work and 1 of them is repeated. Maybe 1 of them works and then the other 2 zeros are irrational, maybe. Don't know. We'll find out. So again, you could go ahead to your calculator and find one that automatically works. In fact, I'll show you that. Or I just start with the 1, then the -1, then the 5, then the -5. But let's say you are the student just using the calculator as an assistant, not doing everything for you. So x cubed minus 4x squared plus 8x minus 5. Go to graph. And I'm not saying that this window is always perfect. You may have to expand this. And maybe this isn't the whole picture. So if you look here, I can only see 1 0. Now maybe 2 of the other zeros are like over here. If you extended this over here, maybe there's a 0 here and here or something like that. Maybe this thing eventually does this. I don't know. But let's just go with what we have so far. So that's clearly a 0. Let's hope it's a nice whole number. Otherwise, we're going to have to play with the window. It looks like it's in the ballpark of 1, which 1 is a possible rational zero, so that's hopeful. Boom, it works. So positive 1 should work. It is very obvious that -1 does not work. It is very obvious that 5 doesn't work, and it's very obvious that -5 doesn't work. So out of our 4 options, only one of them is going to work. Maybe it works multiple times, maybe not. Let's just start this and see where we get. So there's our positive 1. To the right, we go 1, -4, 8, -5. Bring down the first 1. Multiply 1 times 1 is 1. -4 plus 1 is -3. -3 times 1 is -3. Also, if I'm going too fast, watch YouTube and hit the slow down button, the playback speed. 8 minus 3 is 5. 5 times 1 is 5. -5 plus 5 is 0. Our calculator confirmed it. And that's the only time I'm using my graphing calculator. I'm not, honestly, it won't even tell me the other zeros if I tried to. But again, this is the point where you're supposed to be done with it. It was just supposed to give you a push in the right direction. So now we know that the quotient, again, from right to left, that's remainder, constant, coefficient of x and x squared. So it's 1x squared minus 3x plus 5. So we know x equals 1 is a 0. So x minus 1 is a factor, which means now f of x can be written as x minus 1 times the quotient of x squared minus 3x plus 5. And remember, the whole thing is that we're setting this equal to 0. We're finding the zeros. If I told you to factor it, you find the zeros and then factor it implicitly, basically. Well, x squared minus 3x plus 5, spoiler alerts, that's prime. There's no factor pair of 5 that adds to 3. It adds to 6. It's the only one option, 1 and 5. So we got a quadratic formula it, with an a being 1, a b being -3, and a c being +5. Can I fit that all there? I don't know. That might get a little ridiculous. So x equals -b, which is -3, plus or minus big square root, b squared, which is -3 in parentheses squared, minus 4 times a, which is 1, times c, which is 5, all over 2a, which is 2 times 1. Arithmetic, arithmetic, arithmetic. -3 is +3, plus or minus square root. -3 squared is +9. 4 times 1 times 5 is 20, so that's -20, all over 2. 9 minus 20 is -11, so that's 3 plus or minus square root of -11, all over 2. And we don't know the square root of -11 exactly, because we don't know the square root of 11. We can't break up 11 because it's prime, so we can't even do that 4 times 5 business like a previous example. But we can do one little thing. The square root of a negative means you have to pull out an I. That's 3 plus or minus I square root of 11 over 2. That's as far as you can take it. So that's your other two zeros. X equals 1 was the first one. So there's the separated answers, but if you want to put them all together, that means you get x equals 1 comma, and then 3 plus or minus I square root of 11 over 2. In my math lab, once again, you'd have to go 3 plus I squared 11 over 2, comma, 3 minus I squared 11 over 2. Unless they've changed something in the code. 3 zeros, that was a third order polynomial, so that's a good sign. Now notice something, this one's got an I. Remember, imaginary numbers, you can't see their zeros. That's the whole reason they're called imaginary. It's not that they're fake numbers, it's that their x-intercepts, aka their zeros, are not real. This has an important value to it, it's just visually not there. So that says that graph that we had earlier, even if I did, pull back on this, if I made the window maybe from -1, just 10,000, I guess, to 10,000, you're still only going to see 1 0, and it's going to be right around here if it's even visible. And I've pulled back too far, so it's not visible, unfortunately. But if I hit trace, or is it still drawing it? There we go. If you type your 1, you can still see that it's 0, but it just gets ridiculously large really quickly. Yeah, it never crosses the axis anywhere else except for there. So if you try and use your calculator to cheat this problem, you're only going to find one of the zeros, and my math app's going to mark it wrong. And guess what I like to do? I like to throw at least one question on the test where that would happen. So not only do I have a way of going back to your work and penalizing you for using a calculator too much, I also have a way of making problems so that even if you are using the calculator too much, you're going to make a mistake. Your calculator isn't supposed to do everything for you. You have to show your work, because that work is going to pick up zeros that your calculator may not have picked up, as well as your teacher said the work's as important as the zeros themselves. All right, so we do not have time to start D, so we'll go ahead and call it there. But I will mention that D, ignore all that stuff below, this one is going to start out as an x to the 4th. And then there's going to be other terms. This means that we're going to ultimately end up with 4 zeros, maybe some multiplicities, that's always a possibility. But it means that this whole synthetic division testing process is going to happen more than once. With cubics, after you do it once and find a 0, you always get down to a x squared, and then you don't have to do it anymore. But this x to the 4th, after we find our first 0, it's going to be an x cubed, which means we're probably still going to have to go through the process one more time. So that's your warning for next class. So next class, we will definitely finish up 3.4 since we only have this one more problem plus just a couple extra notes down here about knowing zeros and finding a factored form. And then we'll be able to go in 3.5. So we only have 2 sections left in this, this section. We're not going to do 3.6, and we're also going to be trimming the fat on 3.7. So I said I'd talk about test 3. It's going to be 3.1 through 3.5 and 3.7. We did 3.6 back in test 1. In 3.5, we're going to be trimming the fat on this. We're only going to do asymptotes. The ultimate goal of 3.5 is to graph rational functions, which is a whole new beast. And it's an important concept that if I find after we finish chapter 4 that we have time to do it, I'll come back and do it. But we lost a whole week due to just complications involving what power outages, me being sick or something like that. I don't even remember at this point because I had different classes missed between my Tuesday, Thursday versus Monday, Wednesday. So just note on the test, we're not going to talk about the full graphing concept, just the asymptotes. All right. Now that test, if we fail.
All right. So we're going to talk about the test date next time. But for now, 3.2 and 3.3 dates you can see on the board. We'll officially assign 3.4 next time, which means it'll be due a week after that. But we still had that one more example to do, so I didn't want to rush that too much. So have a good one. We will see you Thursday. Email me if you have any questions, as always. Take care, everybody.